All right, so we have now started our first topic in physics, and that topic is called, or as physicists would call it, it's called kinematics. Now, kinematics is a fancy word for the study of motion. And we're going to start off with what's called 1D kinematics. The word 1D means the motion is along a straight line. Now notice if you have a straight line, kind of like the underline this word is written on, you can stay on that line while still moving in two different directions. I can move to the right or I can move to the left. So although I have two different directions I can go in, this is still considered 1D motion. There's two directions, but there's only one dimension, one straight line. So that's what we're going to study for the next few lessons, is 1D kinematics, or motion along a straight line. An example of this would be if you have a car that's driving down a straight section of road, maybe speeding up or slowing down. Or if you have a ball that you throw straight up in the air, and it goes up, reaches the top, and then comes back down. Those are both examples of motion along a straight line, or 1D kinematics. So now that we know what vectors and scalars are, and we have a bit of a sense of distance and displacement, I want to just quickly review those two topics. So distance, in the last lesson, we said was a scalar, and displacement is a vector. We said last lesson again that distance is how far something travels along the path it took, whereas displacement, also called the change in position, can be thought of as a straight arrow from start to finish. So if I want to know the distance of something's gone, I need to watch the path that it took. If I want to know its displacement, all I need to know is where it was at the beginning, where it was at the end, and I don't care where it went in between. And we saw an example last day where although these are both measured in meters, an object had a different number for distance than it did for displacement. So although these two are very similar and sometimes are used interchangeably, although incorrectly, they can be different, and that's an important distinction to make. Now, we want a short way of writing these out so we can put them in equations without writing the whole word. So we're going to come up with a symbol for them. And conveniently, since they both start with D, we're going to use the symbol D. However, since we know that they're slightly different things, we should have slightly different symbols for them. So I'm going to put a little arrow over top of this D. That arrow reminds me that this displacement is a vector. It has not just magnitude, but also direction. So if you see D without an arrow, that means we're talking about D the scalar, which is going to be distance. If you see D with an arrow, that means we're talking about D the vector, and that's displacement. This arrow is called a vector hat. Okay, so after that quick review, let's introduce the two new ideas for today. So the next two quantities we're going to look at are kind of similar to these two. They are quantities that people often get mixed up with each other. You've probably heard people use the word velocity in your life, and often when they use it, they actually mean speed, and they're just trying to sound fancy. But velocity and speed are actually different things. There are some important distinctions between them. So just like with distance and displacement, we have one scalar and one vector here. Speed is a scalar, and velocity is a vector. The easy way to remember these two is speed and scalar both start with the same letter, and velocity and vector both start with the same letter. Now, again, we're going to want to be able to use these in formulas. We don't want to write the whole word out every time, so we're going to come up with a symbol for them. And we're going to use the symbol, just like we used V or D for both of these, we're going to use V for both of these. But again, the one that's a vector is going to have a vector hat on it. Now, distance and displacement were pretty easy to figure out. We just kind of watched what the object was doing. We measured some stuff, and we were able to just kind of count the distance and figure out the displacement by looking at where it started and where it finished. Speed and velocity are a little harder to measure, to figure out, unless you have a sophisticated device on the object that's directly measuring these things. So we'll find more often we actually have to calculate these values rather than just observing them or measuring them directly. So I'm going to give you a couple of formulas that we can use for calculating speed and velocity. Now, a lot of the time when things move, they will speed up and they will slow down. Like the example I gave before of a ball going up in the air and coming back down. It's going to be slowing down on the way up and speeding up on the way down. So asking what's the speed of that ball is kind of an impossible question to answer because the ball has many different speeds. Asking the distance that ball went is pretty easy. I can figure that out even if it sped up and slowed down along its path. But asking the speed is a bit more nonsensical because it had many different speeds. So finding this speed at a specific point is a little trickier. What I'm instead going to give you a formula for is a formula for the average speed of an object over a period of time. In previous courses, you've probably learned that speed is distance divided by time, and you've done calculations with that. This is just the exact same formula, but we're being a little more specific here. It's technically average speed, that's distance divided by time, and we're using proper physics symbols for speed and distance and time. Now, you likely have not seen this little guy before. This is actually a letter, but it's not a letter from our alphabet. It's a letter from the Greek alphabet, and it's called delta. So this triangle is the Greek letter delta. And it means the change in something. So, for example, if I have a fruit bowl, and one day it has 4 apples in it, and the next day it has 3 apples in it, I could calculate delta apples, or the change in apples, and I would find that it's -1. It had 4, now it has 3, so it's down 1 apple. The change was -1. And the way, those are pretty simple numbers to work with. But the way I got -1 was I did the final number of apples, 3, and I subtracted the initial or beginning number of apples, or 4. So the final number minus the initial number gave me the change in the number of apples. 3 at the end minus 4 at the beginning gave me -1. And so this is a minus sign. So this is a symbol that's going to come up a lot in physics. It's the Greek letter delta. It means the change in something, and we calculate it by doing final minus initial. So over here where it says delta t, this is the change in time, how much time passed while the object was moving. So I often tell, students sometimes are used to just seeing t at the bottom here. And they're like, why do we need that delta? I say, well, if we just had t, people might think we're plugging in the time, like the time of day. So if an object is moving at 3:15 p.m., we would put in 3:15 p.m. down here for the time. And that's a difficult number to divide by. It doesn't necessarily make a lot of sense why we would use that either. So it's not the time of day that we want. It's how much time has passed while the object has been moving, the change in time. So if it started moving at 3:15, but it ended moving at 3:16, the change in time would be 1 minute. Okay, so there's my speed is distance divided by time formula to calculate speed. But again, we're being particular here. It's change in time we're using down here, and this formula actually tells us the average speed, since objects can quite easily speed up and slow down while they're moving. The formula we have for average velocity basically starts out exactly the same. Only because velocity is a vector instead of a scalar, we got to put the vector hat on this v. So this says average velocity instead of average speed. And because velocity is a slightly different thing than speed, we're going to have to calculate it slightly differently. And we're going to do that by using displacement instead of distance. So taking this formula, adding two vector hats to turn this into velocity and this into displacement, gives us a new formula. Okay, so now I want to just try an example with you guys that will sort of illustrate a couple of things you might run into, and we can talk about how to deal with them. So this example uses one of our new formulas. We have a car that's traveling at 45 kilometers an hour, and we want it to travel 100 meters, and we want to know how long that will take. So, looking at this question, it's giving us a speed and a distance, and we want to know how much time passes while that's happening. We have a speed and a distance, and we want to know delta t. So, let's start with this formula. Now the thing I'm looking for here is delta t. So the first thing I should do is rearrange this formula to isolate delta t. Now the tricky thing is delta t is on the bottom of a fraction. It's impossible to isolate something if it remains on the bottom of a fraction. When we isolate something, we need to get it on the top all by itself. So right away, I'm going to try and deal with the fact that delta t is on the bottom. And I'm going to get rid of the delta t on the bottom by multiplying both sides by delta t. If I do that, I get VAV times delta t equals d. Okay, now again, here's that delta t I'm trying to isolate. It's getting multiplied by VAV. I want to undo that, so I'm going to achieve that by dividing by VAV. And I have to, of course, do the same thing to both sides. So this gets me to delta t equals d over VAV. Okay. So now that I've achieved this formula, I should be able to just kind of plug some stuff in. I know my distance, 100 meters. I know my average speed is 45 kilometers an hour. But there is an issue here. It has to do with units. The best sort of habit to get into regarding units when we're using physics formulas is to always use metric base units when you're plugging numbers into a formula. So metric means avoid things like hours or inches, and base units means avoiding prefixes like kilo. So to get this to metric, I'm going to have to get rid of the hours, and to get it to metric base units, I'm also going to have to get rid of the kilo. So how do I, in other words, I want to get this from kilometers per hour into meters per second, the metric base unit for speed. So you may recall, we talked about this earlier, the shortcut to go from kilometers per hour to meters per second is to divide by 3 8.6. And if we do that, we get 12.5. Okay, so now I can plug numbers into this equation. The distance the car traveled was 100 meters. Because that's metric base units, meters, I'm happy just plugging that number straight into my equation. And the average speed, well, it only tells us it was going 45 kilometers an hour. So it doesn't mention speeding up or slowing down. So we can assume it was going that speed the whole time. So that will be its average speed. And again, we'll take the version in metric base units and plug that in. This gives us an answer of 8, or 8.00, if we want to use 3 sig figs. The nice thing about always putting metric base units into an equation is that I know I'm always going to get metric base units out. So I don't even really have to go in and figure out, oh, what would meters divided by meters per second be? Although I can do that, I can just say, hey, I was solving for time. The metric base units for time are seconds, so I know I'm going to get seconds when I'm done this. Okay. So, a couple ideas there that I wanted to expose you guys to. One was always checking that you have metric base units before plugging numbers into an equation. So we looked at that by converting this 45 into meters per second. And the other thing I wanted to show you was when you're rearranging an equation, to isolate something that's on the bottom, you got to make sure you end up with having that thing on the top. It's not isolated, even if delta t, even if I move the d over, if delta t is still on the bottom by itself, it doesn't count as being isolated. All right. Let's look at an example that kind of illustrates the difference between distance, displacement, speed, and velocity. So I've got two colors here that I've been using, blue and red. Let's talk about a race between a blue character and a red character. We'll call them red and blue. So they're both going to start at the same place. But blue is going to run 10 meters to the right, then turn around and run 5 meters left. So let's draw that out here. Here's my blue person. And they are running pretty fast. And they're going to run 10 meters to the right. Then turn around and run 5 meters to the left. Now, my red character is going to start at the same position, but they have a handicap in this race. They are only allowed to walk. Red is not allowed to run. However, they don't have to go as far as blue. They can go straight to the finish line without overshooting. They can just do 5 meters to the right, but they have to walk. So I've done this experiment in class with students a few times, and you can imagine what might happen if we did this race. Generally, the person who has to go only 1/3 of the distance generally wins the race. They might have to walk a little bit fast, but it's pretty easy for this person to get to the finish line before blue has gone all the way across and back. Blue also has to go. There's a lot of time wasted over here while blue slows down and then speeds up again. So let's say in our example, blue is able to do this whole race across and back in, let's say, 4.5 seconds. But red beats blue by a little bit. They don't have to go nearly as far. They don't have to stop and turn around and change direction and speed up again. So maybe red can do this in 4.1 seconds. Okay, so what we're going to do is we're going to calculate the distance, displacement, average speed, and average velocity for each of these characters. So here are going to be the calculations for blue, and here are going to be the calculations for red. Okay, so the distance blue traveled, remember distance is how far something traveled along the path it took. So if we trace out blue's path, we do 10 meters and then another 5, which is a total of 15 meters. And if we look at the distance red did, well, again, tracing along red's path, we see that red did 5 meters. Now let's look at their displacements. Remember, displacement is a vector, so it needs direction. And displacement doesn't depend on path. It just depends on where you start and where you finish. So blue started here and finished here. If I draw a straight arrow from start to finish, that arrow is going to be 5 meters long, and it's going to be going to the right. So blue's displacement is 5 meters right. Red's displacement, well, red started here and finished here, so red's displacement is also 5 meters to the right. Straight arrow from start to finish. So my vectors have a magnitude and a direction, and my distance, my scalar, has just a magnitude. Okay, so now let's find their average speed and their average velocity. And we'll see if these numbers that we calculate jibe with kind of what you would expect. So you guys probably have a good sense of what speed is. And in this question up here, if I asked you which of these racers has more speed, you'd probably say blue. Blue's the one who's allowed to run. Red's not allowed to run. So blue's probably going to be the one that has more speed. Let's see if our intuition about speed jibes with what our equation is going to tell us. So speed, we said, is distance over change in time. Blue's distance was 15, and that's metric base units, so I can plug it in like that. And blue's time was 4.5 seconds. Again, metric base units, so I can plug it right in. So 15 divided by 4.5 gives me 3.33. And because I made sure I was putting metric base units in, I know I'm going to get metric base units out. And metric base units for speed are meters per second. So blue's average speed is 3.33 meters per second. Again, blue's speed will be different. He'll start slow, he'll speed up, he'll slow down here, he'll speed up again, and then he'll come to an abrupt stop at the finish line. So it's hard to say blue's speed is this, but we can say what blue's average speed is. Now let's do the speed for red. Again, average speed is distance divided by change in time. Red's distance is 5 meters. Red's time was 4.1 seconds. So we get 1.22. And notice I'm leaving both answers here to 3 sig figs meters per second. So, as you probably anticipated, the racer who was allowed to run ended up having a higher average speed than the racer who is constrained to only walking. So speed behaves as we kind of thought. Things that go fast have more average speed. All right. Now, let's look at velocity. I said before, velocity in daily life is often just a word people use when they mean speed, but they want to sound fancy. But there's more to it than that. So let's look at it. Blue formula for velocity, or for average velocity, the vector hat, is displacement divided by delta t. Now, blue's displacement is 5 meters to the right. Now, this right part is important. This is what makes this a vector. And we definitely need a vector in this formula. So how am I going to put this into my calculator? Well, what we're going to do is we're just going to say that vectors that are going to the right, we'll use positive numbers for them, and vectors that are going to the left, we'll use negative numbers for them. So I'm going to plug 5 into my calculator, but I'm going to make very sure that it's a positive 5. And I'm going to write that positive in there as a reminder that I've intentionally chosen this to be positive. It could have been negative if it was left, but this positive tells the calculator that this was not just 5, but 5 to the right. And again, the time for blue is 4.5 seconds. So that gives me 1.11. But again, I'm looking for average velocity, which is a vector. So the thing I get out should have direction. When using my calculator and I have this agreement that we're going to use plus and minus to communicate direction. So I should be careful when I take this number out and think, wait, was the number my calculator gave me positive or negative? And indeed it was positive. So positive 1.11 for a velocity means 1.11 meters per second, and the positive means right. Let's do red. Okay, average velocity is displacement divided by change in time. Red's displacement was 5 meters to the right, so positive 5. And red's time was 4.1 seconds, so that gives me 1.22. like we had before. But again, because I'm looking for a vector, I have to pay really close attention to whether my calculator gave me a positive or negative number. And indeed it was positive. So how do I interpret this? Well, the 1.22 means 1.22 meters per second. And the positive means the direction is to the right. So here's where maybe your intuition about velocity doesn't quite pan out. We see that although we got the sense that blue had a much higher speed than red, and we calculated that, indeed it turned out to be true, blue did not have a higher average velocity than red. Blue's velocity is actually a little bit less than red's. Because for average velocity, it doesn't matter what path you take. All that matters is where you start and where you finish. So because blue and red actually started and finished in the same place, they both had the same displacement, but because red got there slightly sooner, red's average velocity was more. So this is an important thing to realize, that velocity and speed are different. Velocity is a vector, that's one difference, but velocity is also calculated in a different way. And there can be times where a fast object doesn't actually have that much velocity. That's all for this lesson. We'll see you in the next one.